Okay, hello, welcome to my channel. Now in this video, we want to find the limit of this function, the limit as x tends to 0 of sin of x over x, alright? So this is a limit of a special function. Of course, we know the result to be 1, okay? But a lot of people go ahead to evaluate this limit by using the L'Hopital's rule. That is completely wrong, alright? Yeah, it's a wrong approach because you are doing what we call circular reasoning, you know? Yeah, in the process of using the L'Hopital's rule, you will have to differentiate the numerator and denominator with respect to x, since the limit is going to give us 0 by 0 in indeterminate form, alright, by substitution. So in differentiating sin of x, we get cosine of x. But if you look at the process of deriving the derivative of sin of x, we are demanded, or it is required of us to know the limit of this special function before we can know the derivative of sin of x, which is cosine. Okay, so because of that, we are not going to be doing L'Hopital's rule, alright? Because using L'Hopital's rule means we already know what this limit is. And if we already know that, what's the point solving it, alright? Okay, but here we will help you to show yourself approved. Alright, great. So what I'll be doing here will be to apply the Squeeze Theorem, which tells us that if you want to find the limit of a certain function, then we can find other functions that, more like functions that bound this function, right? Yeah, a function that is less than this particular function and the other one that is greater than it. Now if you have, okay, let me put it this way, if you want to find the limit of this function f as x approaches a certain constant, right, let's say c, okay, and you can find other functions, let's say g and h, okay, such that this holds, right, that is g is on the left hand side of f and then h is on the right hand side of f, right, that is f lies between the two of them. Then if the limit of these two as x tends to the same result at the same value c is the same, if the limit remains the same, then the limit of this one is the same thing as the limit of the function at the boundaries, okay, or on the edge of f. Good, that's just the Squeeze theorem. So what we want to do is to try to get a suitable function such as g and h, okay, so that if their limits are the same, then we can say the limit of the middle function, which will be this function here, that is sin x over x, is going to be the same thing over like that. Okay, great. So let's see what we're going to do. Well, I'm going to start off by using a unit circle. Okay, so let's have this. Let's have a unit circle, not just the whole thing. I just want to look at the first quadrant, right? Yeah, so let's have a circle like this. It's supposed to be a full circle. By unit circle, mean radius is equal to 1. So from here to here is 1, and then from here to here is 1, right? Yeah, 1 unit, whatever the unit is. Now we look at x approaching 0, and since we have sin of x, x can be seen as an angle, right? So let's think about x as an angle. And since x is approaching 0, let's say if it's small angle, right? Okay, great. Now here I'm going to be taking x to be approaching 0 from the right. Then we are going to see how that corresponds with x approaching 0 from the left. And the reason why that is so is because as x approaches 0 from the left, okay, for the limit to exist, we should think about the left hand limit and then the right hand limits, okay? So as x approaches 0 from the right, is the result the same thing as when x approaches 0 from the left, okay? So we want to compare that. So we first of all start with when x approaches 0 from the right. So that means the angle will be positive, right? But maybe approaching 0, so let's just make it big enough so that we can see what we want to do here. Okay, great. Now look at this from the line here, right? Yeah, that is the line produced by this angle, okay? We can see that we can draw a vertical line from here to here, okay? That is just to make that a right angle triangle. And then let's draw another line. We call it a tangent line. Let's draw a line tangent to this curve at this point 1. Okay, you notice that this is a unit circle, which means the radius is 1. So from here to here is 1 unit, right? So this place is 1, but I've already written the whole measurement here. So a line tangent to this circle at the point 1, 0, right, on the circle. Okay, so this is a tangent line. Then we are going to extend this line so that it touches this tangent line at that point. Okay, now let's get our measurements ready. Okay, so since we have this to be the tangent line, let's just call it T, that is from here to here, and then we have this arc formed from this angle x, alright? Okay, so we are going to try to look at the length of that arc, and then we have the other side, that is the opposite side to the angle, right? Okay, maybe let's just call that h. That is the opposite side to the angle. Let's call that h. Okay, so you know that the blue arc is going to be formed. All right, so let's see how we can solve for, oh, I don't want to clean this. Anyway, I've already talked about it. Anyway, let's see how we can get the h, the arc length, and then the t. All right, so maybe let's just call the arc length L. Okay, yeah, let's just call it L so that we know what we're doing. All right, so how do we get the arc length? All right, so when you have a circle, okay, you have a certain arc, then the radius bounding the arc times the angle that produces the arc will give us the length of that arc. In other words, the L will become the radius, which we say this is a unit circle, so it's going to be 1. This is the length of the arc, that is L, times the angle that subtend the arc. Okay, yeah, the angle that produces the arc, that is x. So in other words, we have this length to become x. All right, okay, so let's look at the tangent line T. The tangent line from this point to this point. All right, so to look at that, to think about this as a straight line, that is the hypotenuse side, then we think about this as a bigger right angle triangle. This one bounded by the red line all through, by the black line all through, is a smaller right angle triangle, right? Okay, so to get this T, we need to think about this as opposite over adjacent, right? That is T over 1 is going to be the same thing as tangent of x. Okay, this and that's what we know. We do not know what the length of this line will be from here to here, but we know up to this point, which is 1, but we don't know the remaining part, so we cannot use that. Rather, we use 1 and t, which can be gotten from the tangent. So tangent of x is going to be t over 1, which means tan x is t over 1. That is, t is tan x, right? So we can call that t, just write it as tan x. Okay, great, that's nice. And now let's think about the last one, which is the h. Okay, the hypotenuse side, as I said, for the smaller, no, not the hypotenuse side, the height for the smaller right angle triangle. Okay, so we notice that for x here, we do not know the measurements from here to here. We only know from here to here to be 1 because of the unit circle. But we know the measurements of here to here to be 1 because of the unit circle. So in other words, we can make this of opposite to the angle and then the hypotenuse side, which tells us about the sine. So we can call h, let me put it down well. Okay, so we're going to call h to be sine of x is h over 1, which is just sine x is h, right? Okay, so this is h equals to the sine of x. Oh god, the marker is not writing properly. Okay, h is equals to the sine of x. Okay, all right, that's good. So we've set up what we want. Now you notice that just by looking at it, it is clear that the t line, that is the tangent line from here to here, is longer than the length of the arc formed, and the length of the arc formed is longer than the h. All right, so in other words, we can say the h is less than the length of the arc, which is less than t. But since this x is not just a constant, it is a variable approaching 0, right? Of course, we said we are starting from the right as it approaches 0 from the right. So since it is approaching 0, it means that this can somehow be equal at some point. So this is what we are going to do. We're going to start off by saying h, okay, is less than or equal to, let's see, we're going to say h, okay, is less than or equal to L, and then the L itself is less than or equal to T. That's how you're going to set it up, right? Then what is h? Well, by substitution, we notice that our h here is sine of x. So I can say sine x, right? Sine x is less than or equal to L was gotten to be x itself. So we say x, which is less than or equal to t, which is tangent of x, right? So we can call that the tangent of x. Okay, great. Now what we want to do is to try to get this function. You notice that x is lying in between sine and tangent. Well, what we want is sine x over x. So let's try to make sine x over x to lie in between two things, all right? By getting the sine x over x from this middleman here. So that's just what we're going to do. Okay, so we start off by simply dividing through by sine. We're going to have x over sine, right? So when we divide through by sine, we're going to have sine x over the sine of x, like I said. And then that is less than or equal to x itself divided by the sine of x, divide through by sine x. And we are not changing the order. This is tangent of x. Coming to that, divided by sine of x. Now we are not changing the order because as x approaches 0, sine of x remains positive. As x approaches 0 from the right, you know, from the curve, the graph of the sine function, it goes like this, the sinusoidal curve. Okay, so as we approach 0 from the right, the result is positive. So dividing through by a positive number, we don't change the order of the inequality. Alright, okay, so you notice this and that will give us 1. When we divide, we get 1 as a result. Then this is less than or equal to x over the sine of x. Nothing will cancel out there. Then this is less than or equal to, well, tangent of x is the same thing as sine over cosine. That is tangent. Then we divide it by sine in the bottom. So we are going to be left with 1 over cosine when we are done dividing. Right? Yeah, that is it. Now, again, we want to take the reciprocal. Should I say, we want to invert each of these terms here. Okay, so you notice that we have a term. If you invert it, the order will change. The order of the inequality will change. So that means it's going to turn out to be 1 over 1. By inverting, we're going to have 1 over 1 is greater than or equal to sine over x. Right? Yeah, so when you are multiplying through the inequality through by a negative number, dividing through by a negative number, or you are inverting, like taking the reciprocal, you have to change the order, right? Okay, so now we have our desired function at the middle. We have extreme functions. We can now use the Squeeze theorem. Okay, what does it tell us? It tells us that to determine the limit of the middle function as x approaches a certain value, okay, take the limit of the extreme functions, and these are really easy to take as x tends to 0 from the right. And if the results are the same, then the result of this middle function is the same thing as the others. So as you can see clearly, the limit, okay, as x tends to 0 from the right, and we will also look at when x approaches 0 from the left, of 1. This right here is equal to 1, alright? And then we look at the limit as x tends to 0 from the right of the cosine of x. Of course, cosine of 0 is 1. So since the function is continuous, let me not go to that. Since this exists is equals to 1, this one is a constant, the limit as x tends to anything will remain the same. So that means that the limit of this one is just 1. Okay, and the limit of the extreme right hand side is also 1. Therefore, this middleman must be 1. That is to say, the limit, okay, limit as x tends to 0 from the right, don't forget that, of sine of x over x itself is equal to 1. Whew. But we are not done yet, because this is just the right hand limit. We want to also look at as x tends to 0 from the left. If the results are the same, then we say that the limit exists and it is equal to 1. So we just have a little more thing to do. But that is not really hard to see from here. Notice that, let me just bring in an absolute value stuff. Well, we have, if x is negative, that is to say, as x approaches 0 from the left, okay, notice that x can be written as negative of the absolute value of x, right? Absolute value of x ensures x is, this is positive, then the negative will mean it to be negative, right? Yeah. So what are we to do? Anyway, I can easily replace x itself as we approach 0 from the left with negative absolute value of x. You notice that approaching 0 from the left means very small negative numbers, right? Yeah, that is, this is 0. Just before 0 from the left, that is just negative number like negative 0.1, negative 0.0001. So very small but negative numbers. Okay, so in that case, let's replace x with negative absolute value of x. All right. So if you do that, notice that here is going to become negative absolute value of x. All right. That is sine of that. Then negative absolute value of x. Tangent of negative absolute value of x. Sine is an odd function. All right. Yeah. Okay. Maybe let me come over here. Sine is an odd function, which means the negative will come out here. We have absolute value of x, which is just positive. This one, cosine, is an even function. The cosine of a negative input is the same thing as cosine of the positive version of that input. Alright, so we have that. Now, as this tends to 0, as the x tends to 0 from the left, 1 remains 1 because it is a constant. As x tends to 0 from the left, cosine of something tending to 0 from the left, this is the cosine curve, right? Let me see. Come over here. Yeah, it's symmetric about the y-axis. So as x tends to 0 from the left, okay, the result is also approaching 1. That means the limit of this is also 1. 1, 1. So the left hand limit is also going to be 1, which means the result here is exactly equal to 1. Right? Yeah, so you can just get it that way using the unit circle, right? The idea is to get functions, is simpler functions that you can evaluate as a bound, then you'll get your result, right? I know in the end I mixed some little properties of sine as an odd function and cosine as an even function, but it's not too bad to see. You can do the entire process again using the fact that x approaches 0 from the left, and you still get the same result. Okay, I hope you enjoyed the video. Thanks for watching, and don't forget to subscribe to my channel, share this video with your friends, alright? And I'll see you in our next video.